the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 71, where today we are going to be talking about statistics.
Mm-hmm.
Yep.
And statistically speaking, this should not be our last attempt at recording this podcast.
Yeah, we have attempted at recording this podcast a few times, actually. The beginning has been a little choppy, but here we are. So statistics. For those of you that have been a little avid listeners of the podcast or at all, might know that I'm actually majoring in statistics. So I'm very excited for this episode today. And Parker has some mixed feelings about it.
You know, it's all right, I guess.
Yeah, so today's episode, let's get into it.
Yeah. Well, first of all, we should probably do that intro that we did on the other ones, on the other attempts.
Oh, well, first of all, big news. Before we get into it, check out our Instagram because our giveaway is live. We have one more week ending next Friday. So this is going to come out Monday, so about 5 days. Go on our Instagram, math.physics.podcast. There's a post where it has the giveaway rules. Just share our post, tag a few friends and your favorite episode number. And basically, we're just going to do like a random comment generator. And boom, whoever wins it, wins it. It's going to be so much fun.
That's right.
You guys pick the shirt. So I'm super excited for it. So if you guys, want to win it, want a chance, go to our Instagram page and, go check it out.
Yeah, and we are like, it doesn't matter where you are in the world. We'll just ship it to wherever you are. And we'll do it like, we'll make the shirt custom and everything. Just tell us the size. And then boom, we'll make it, send it over. So yeah, make sure to go and enter the giveaway. It's officially live. I don't think we have that many entries. I think there's like 30 entries so far, maybe a little bit more.
35, I believe. I think we have 35 entries, right? It's like somewhere around there. But yeah, let's see. I mean, who knows? We still have a whole, the day we're recording this, we have like 6 days when it's going to come out, 5 days. So let's see, Maybe people who listen to this go on our Instagram, go get that shirt. Who knows?
Definitely.
Yeah.
So before we get into the podcast,
let's get into
the
news, right? Let's get into the news. So downloads, we're actually almost sitting at 175,000 downloads right now.
Dang.
I believe we're at 174 something, but thank you guys, man. We're so close to that 200. It's going to be really cool when we do. We're always improving, thanks to you, obviously. And on Spotify, that weekly update, we're sitting at 11.5 thousand followers.
Damn.
So
also
that's really
something
cool.
that's interesting. On Monday and Tuesday.
Yeah.
On both days we got like 1,100 downloads, which was the most we've ever gotten, and we've gotten that twice in a row. So that was cool.
That's decent. That's decent.
Yeah.
Good stuff.
Yeah.
Thank you to all of our listeners, as always, for continuing to tune in. And we do this for you.
Yeah, and especially right now, make sure to send us some episode suggestions.
Yeah.
Because we come up with a topic kind of like on the spot almost.
Literal random. Just random. Like, hey, what do you want to do? Yo, what about this? Short.
Yeah. And then we
That's
talk
the whole
about
planning.
it for a bit.
That's the whole plan. Now, obviously, like we do work into the podcast, but the topic itself, fully just randomized. So,
for sure. Anyways.
Always accessible on Instagram.
The comment of the week.
Let's get it.
This week. Make sure to leave a comment under this video if you want to be next week's
underneath
comment
that like button
of the week. But this week's comment comes from Bernice.
Nice.
Not sure how to pronounce it. Anyways, they say it's like a long comment. I'm not going to read it all, but essentially they said that we had a great episode and that there's a lot of value in our podcast because, they're a math tutor. And so the things that we say gets passed down to the next generation of mathematicians and all that stuff. So yeah, thank you very much for your great comment.
Mm-hmm.
And if you want to be next week's comment of the week, make sure to go to YouTube. First of all, leave a like and leave a little subscribe. But
why not?
Most importantly, leave a comment.
For sure.
And you might be next week's comment of the week.
Mm-hmm. Very simple. Very simple to get that status.
Is there anything else?
I don't think there's any more news.
Right.
We did the giveaway. We did the. I think we're good on the podcast on the news front. So let's get into it. Let's get into statistics. Why do we need statistics in the first place? Oh, this is the part that we did on one of the takes.
Yeah.
Oh, this is the part that we did on one of the takes.
Like, okay.
Yeah, I remember. Okay, yeah, this is the part that I forgot about. Yeah. So, why do we need statistics, right? So, the best thing for us in the world of statisticians and mathematics is to do what we have. And what we have is data. Bunch of it. And the best thing that mathematicians, or at least I should say statisticians, know how to do is to use past data, previous knowledge, and assume things about the future. That is the whole study of statistics, basically. To take data that you've obviously already taken, so it will be inherently from the past, and you're assuming something about what will happen. Now, there is a level of uncertainty to it. There is a level of preciseness to it that could be wrong, could be off.
Well,
but
also,
that's the whole idea of studying statistics.
It's not only to predict things about the future, but sometimes you just want to like analyze a situation.
You're
For
right.
example, we
And
had a
analysis
lab.
as well.
We had
Right.
a lab where we had like a population of like 200,000 stars and like some of their properties. And then, of course, we only like analyzed a sample of it. But, it wasn't necessarily to predict anything. It was just to be like, oh, this is the median or the mean size of the star, distance, angular velocity across the celestial
and then you
sky.
can do a lot about stars in that same group or in that same cluster, right? So that's the same thing. A lot of times when people say, oh, there's so many people in the world, or like they make some assumption about the population. That's not because they actually have every single person taking a survey. No, they take a sample of people, and we're definitely going to get into what all these things are, like a random sample and stuff like that, where they take a sample of people, and then based on those properties and those analysis, that analysis, they assume things for the population. That's the whole idea. You take a sample and you assume for the population. That is basically the study of statistics. And the reason it's important is because it's seen everywhere. If you ever want to hold a good argument up against anyone, you're going to need some form of statistics somewhere, right? You're going to need some sort of argument, some sort of number, some data that represents some event happening that goes in or against your favor, right? So the whole idea is basically just data, taking in data and summarizing it in some way depending on what we need from it, right? Study of statistics right there.
Yeah, and also one thing that I want to talk about is like normal distributions as well as like the z-score.
Oh,
you know
yeah.
what that is, right?
Yeah, of course. Of course.
Which is super important and also
gonna get into
very, like, it's so easy, quote unquote, to like find a z-score, and it tells you so much good information.
Yeah,
right?
a lot.
We're going to talk about that. But the first thing that we're going to talk about is events. And
Simplest thing.
Rayhan, kick it off.
Simplest thing, event. Well, what is an event? So the whole idea, before we even get into like actual statistics, right? Actually like analyzing the data, well, we have to understand, well, what is the data, right? Like let's dive a little deeper into the actual data itself. So now this is interesting because if you guys have watched the previous episode, which episode 70, which we did with Matt Cater, super awesome guy, super awesome episode. We spoke about some really cool things about functions. And a lot of that is actually relating to what we're going to be talking about today, because a fundamental property about all statistics is a set of events, a set of numbers, a set of something. And the whole inherent property in functions is to take a set and to do something with it, right? Anyways, I'm not going to go into that function thing, but I just wanted to make the relationship between this episode and the last one. But anyways, so the idea behind a set and its importance is we have something called the universal set. In all probability textbooks and all statistics, questions, anything, we have this thing called a universal set, which is basically the set of every single thing that can happen. So let's say, for example, we have only access to 100 numbers, the first 100 numbers. The universal set will be the set that contains 1, 2, 3, 4, all the way to 100. That's the universal set. Now, I'm asking you, I want only the even numbers. So the even numbers will now be a subset of that universal set. And that is what we can call an event. Now, in this situation, any sample, any subset of the universal set can be called an event, right? And the idea behind that is, again, how we define an event is different. So in this case, I can be out of the first 100 numbers. If it's even, it's, the event occurs when it's an even number. So every even number, you will put it into this one subset, and that kind of takes it, right? And then that you call an event space. That's your event space. So again, just diving into a little bit of the nitty gritty of the data before we get into the probability and the statistics, right? And the event space also has something similar called the sample space. A lot of words I'm throwing around here. So a subset of this universal set, right, which contains everything, including the event space, is something called a sample space. Now, this is with everything that you are dealing with in your experiment. So let's say, again, we had access to 100 numbers. And in this particular variation, I am only using the numbers until 50. So the sample will be 1 to 50. And again, this example might not make, you're like, where is any of this going? Believe me, when we deal with populations, it's going to make a lot more sense, right? So a sample is just a part of the universal set, an event, and is basically technically a subset of the sample. It's not a direct a subset of the universal set. Because the idea is, okay, in the sample that we're taking, because remember, we don't always have access to the whole universal set, right? Like in the real world, for example, we don't have access to every single person in the world, but we have access to maybe 100,000, maybe 1,000, right? And we can make an estimation about the whole world. So that's the idea. We take the sample, there's some events in that sample, and these are all just sets. These are all just sets of numbers, sets of information that goes inside, and we're making inferences about all of these sets.
So,
and that's basically the idea.
An event
data
is just any subset
Yes.
of,
Yeah.
and you can give meaning to that event, right?
Yeah.
Like the event could be just a set of all the prime numbers. But
Another example.
But if let's say you're picking numbers, right? And you get a prime number, you don't necessarily have to tie it to that event, right? It's only if you feel like saying, oh, this is a prime number and I'm going to use that to, in the future, I'm going to analyze the data that I got while I was picking these numbers. Okay.
Importance there of all just understanding a little bit about these data before we get into it, right? And continuing on that data front, a lot of these sets, we can now start to analyze them just a little bit again before we get into the nitty-gritty. All sets have something fundamental that we call the mean, the average, right? The mean, the median, and the mode. You may have heard of like the 3 M's, right? Very, very, very common. And not the mode. The mode is really useless, but the mean and the median, at least, very important for analyzing the structure of the set. So what does this set look like? So obviously all of this works only with numbers, right? Like we're not dealing with like cows and dogs putting into a set, right? We're only dealing with these numbers.
But usually,
yes,
everything that you study is tied to a number.
You're right.
You know
what
I mean? I mean, unless you're doing like the eye color of cats,
No, but even that can be tied to a number in the RGB, in the spectrum.
I guess, but the average wouldn't really have a significance because those
maybe
those like results are discrete.
Okay, not in that
like,
example, but I was just trying to say that a number can be
other.
assigned to it. Yes, for sure.
Yeah, no, a number can be assigned, but it's not really the same, right? If you're studying like the height of people in a country, then of course you're just studying, let's say it's in centimeters, their heights measured out in centimeters, and the average or the mean, same thing, is, if you don't know like the mathematical definition of the average, it's, you kind of think, okay, it's like where most people kind of end up. Mathematically, you just add everything up, everything, and divide by the number
exactly
of samples.
The total number. Well, technically, it would be the number of. Wait, what are we? I totally glitched out there.
Is that the average heights?
Yes, the average heights. You would add up the heights and divide it by the number of people that you're taking the heights of, right?
Yeah.
Exactly. Now, you said somewhere there that that's where most of the people will be. That's not always true.
No, that's not
Yeah,
true.
no,
I was just
no, I
saying,
just-
like, intuitively.
Yeah, no.
that
That is, exactly. No, that I wasn't trying to prove you wrong. I'm trying to say that I'm trying to kind of transition into the definition of the median now, because that's not always true. Now, if you have, like, for example, the height, if you have thousands of people, then sure, the average. And now again, we're gonna talk about this, but the average approaches the mean approaches the mean. The median approaches the mean in large samples. The idea is that we have a lot of people, and they could be ranging anywhere from X centimeters to Y centimeters, right? Mm-hmm. Now, if those people are relatively close by, then the average height, right, would be somewhere in the middle. So it would make sense. So let's say one guy was 10 centimeters, the other guy was, again, just random numbers I'm spitting out here. One guy was 10 centimeters, the other guy was 20. The average height is 15 centimeters. And you're like, okay, I mean, that makes intuitive sense. Sure. But now, what if 3 guys are 10 centimeters and one guy is 20? The average gets skewed by that one guy that's 20. Even though most of the people in the sample are 10, 3 out of 4, 75% of the sample is 10, the average is going to be greatly skewed towards 20 instead of 10, right? So the idea, so to prevent this, we have the median. The median is the middle 50% of the data. So while the average, you're just adding up all the data points and you're dividing it by the number of data points, in the median, you list the data points from smallest to largest, and the middle, the bang 50% middle, is what your median is. So in this example, the median would be 10. And you're like, okay, that makes sense. I mean, out of these 4 people, the statistical, what makes the most sense is 10. Mm-hmm. And something you may notice, the median is always a part of the set itself, always. But the mean, well, actually, that's not always true.
That's not true.
That's not always true if you have 2. If you have 2 in the
if you have
if you have 2, you take the mean of it. I was just thinking, because if you have 2 numbers in the middle, right? For example, if you have 4 digits, if you have 4 numbers in a set, there's no half, right? I mean, there's no number in the middle, right? It's just the middle 2 numbers. So what you do is you take the average of those numbers. So I guess, yeah, it's not always in the thing. But the average is rarely ever, if not ever, in the actual set. Because the idea, again, these are just summary measures, right? This is just understanding the data a little bit better. You know what I mean? Mm-hmm, just diving a little deeper into that.
For sure. And one thing, or I guess, wait, are we going to talk about normal distributions right now?
Oh, for sure.
Right now or later?
I mean, yeah, we can get into that like when we talk about like Yeah, I think we're very excited. Let's get into probability. Because I think we can talk about that now. We've gotten to events, right? We've understood what events are. We've understood how we measure sets. We've understood how to analyze sets. Now let's understand, I mean, I don't know how to describe this, but I guess probability.
Yeah.
Let's just talk about probability.
Probability, of course, we got to talk about the coin flip.
Oh, the classic, of course.
So you have 2 outcomes, heads or tails, and a coin, it's very even, you know what I mean? If you want to get very precise about it, technically, one side is going to be heavier than the other because it's slightly, there's more material or whatever.
Yeah, but like
I don't know. Okay.
Smallest amount. But yeah, no, I know what you mean.
Let's just say the coin is even.
Of course, yes.
So naturally, when you flip a coin, half of the time it's going to go one way, half of the time it's going to go the other way. And so the probability, if you flip a coin once, is 50-50. That's just how it happens. But the more you flip a coin, the more different outcomes you have, and then the different outcomes will have different probabilities. For example, if you flip a coin twice, there are now 3 different outcomes if you're not considering like the permutation.
Well, I mean, there can be a head, tail, tail, head, tail, tail.
Yeah, but the
So-
permutation, like the outcome would be like 2 heads, 1 head.
Oh, that's what you mean.
0
Like, because the head, tail, tail, head would be the same. So then there would be
Yeah.
3. You're right.
So if you're just tallying the number of heads and the number of tails
That's
that you
the
have at the
combination,
end,
yeah.
right, the combination, then there are 3 different possibilities, either two heads, 2 tails, or 1 head, 1 tail.
Mhm.
And then because the coin has a 50-50 chance of landing on either side, that means that each one of these permutations is equally probable, and so the combination of heads and tails would be 50% probability, and then the other 2 would be 25% probability. And the same concept applies when you extend the amount of coin flips that you do. If you do 100, then you have like crazy combinations of numbers of heads and tails, but the probability of landing on one single combination will depend on the amount of permutation. This has a lot to do with macro and micro states that we
Yeah,
talked
I was
about
actually just gonna.
in,
This does have, because it's like the number of arrangements.
Yeah, we talked
and stuff
about
like
this
that. Yeah,
in
it does.
the entropy episode that we did, which was a very good episode.
It was a very interesting episode.
Mm-hmm.
But yeah, so probability is inherent in that way, and it depends. Like when we're talking about the number of permutations, number of combinations in all of these events, it tells us again stuff about how these 2 flips are related. And in this situation, we can do that because the coin flip is an independent event, right? We maybe get into independence and dependence, right? Now, that's a really interesting conversation and kind of intuitive as well, right? Like if 2 things would depend on each other, or if 2 things would not depend on each other. For example, flipping a coin the first time and flipping a coin the second time has no dependence on each other whatsoever. So that is why when you simply do it twice and do it 3 times and do it 4 times, that probability or that thing, it stays the same. The pattern stays the same. It doesn't change. But when you start adding different things, for example, let's say you have a vase and you have a bunch of beads in there, right? And you're taking out a bead. What's the probability? Like they're 50 red, 50 blue. What's the probability you'll take out a red? Okay, there's something. You take out a red. But now what's the probability you'll take out a red? Because now there's 1 less red. So that now inherently depends on how many balls you've taken out. So I take 2 balls out. Well, it'll depend on what that second ball was, wouldn't it? So so that's where you get into dependent probability, right? And all of these statements are again talking about the inherent factor about probability, which is sets. So in the classic thing, I don't know when we learned this, but Venn diagrams? When did we learn Venn diagrams? What grade was that?
Like
really
grade
young,
3?
right?
Yeah.
Like really young.
Yeah,
Okay.
very, very young.
So everyone knows what a Venn diagram is. I mean, like that box with the circles over there, like and if they overlap, that means they have similar events. If they if they don't, they're disjointed and they have nothing similar. So that's the exact same thing, right? So these sets are basically these balls and these Venn diagrams that contain information, right? And when we're trying to measure these certain things, we're just either overlapping them. We're seeing, okay, what's the commonality between them? If there's an overlap, that means we're saying, okay, there's some event in this that also happens in this. So both of them happen at the same time in these certain scenarios. Some of them happen independently. Some of them happen together. Again, it would make a lot more sense if you guys kind of can picture that Venn diagram that I'm talking about.
Mm-hmm.
So I'm kind of talking about the things inside the ball itself and then inside the intersection of the ball, right? Because and again, just understanding these relationships between these sets is what is key. At least the bare bones of understanding the probability.
Mm-hmm, mm-hmm.
So yeah, that's
For sure.
basic a little bit. We can move
So,
on
yeah.
to, I think, conditional, like just a little bit, a little bit of this dependency.
Conditional probability, yeah.
Something given something else.
Isn't there a theorem, Bayes' theorem,
Oh, yeah.
which tells you how
Yes,
to
there is.
calculate conditional
So
probability?
Bayes' theorem actually switched the conditional probability. So Bayes' theorem is if you have the probability of an event A given an event B, you can find the probability of B given event A by a Bayes' theorem. That's that like it's a way to swap the probability. So, well, what is that? What did I just say? For those people that might be like, what the hell? Okay, what did I just say, right? So events, if they're not independent, right, they can depend on each other, and then we can give rise to what is called conditional probability, right? Something given something else. Let me give you an example. The probability, let's say we have numbers 1 to 50, the probability that we pick a number that is divisible by, okay, no, that's stupid. Actually, no, that's possible. That is even, given that it's divisible by 3.
Okay.
Something like that. I was going to say 2, but I'm like that.
Yeah.
Yeah. So divisible by 3, right? So that's like an example. So you know that out of this set, I have the fact, given that it is divisible by 3. So out of 1 to 50, I now strip down all the numbers that are not divisible by 3.
Mm-hmm.
And now I say, what is the probability that it is an even number given that it is divisible by 3? So I have all the numbers that are divisible by 3. And now I say, which ones are even? And then I calculate a probability. Mm-hmm. Basically, the number of even divided by the number of divisible by 3. And that'll give you your conditional probability. And again, this works only when the events are dependent. If they're independent events, the idea of a probability of something given something else the other event wouldn't affect it, right?
So hold on.
Yes.
With Bayes' theorem, you would get given it's even, what are the odds it's divisible by 3? Oh,
exactly. That's exactly what it would give you. It would give you so with Bayes. So what you just said. So there's this theorem in statistics called Bayes' theorem, where it's basically, again, I mean, I don't want to repeat the mathematics, but it's basically just a formula that is able to convert these conditional probabilities. So what I just told you, the even given divisible by 3, you would now get, wait, what is the probability that it's divisible by 3 given that it's even? So you just do the opposite thing, and you can do it easily when it's 1 to 50. But when you have discrete continuous distributions, oh my, you can't do that anymore. But I'm just trying to give you like an example of just understanding it basic before we get into the crazy stuff, because there's a lot of crazy stuff.
But what's a real world, like, physical application of Bayes' theorem? Do you know? Like, what would you use that for? Of course.
Let me give you this. We did an example actually in class. Let me give you an example. We have this was the mad cow disease example. We did this in class. So I'm just going to repeat it because it's the one that's in my head anyways. So it's basically each cow either has a disease or doesn't. They can be tested. I mean, and all the cows are tested. It can either be a positive and it's right, or it's a false positive.
Mm-hmm.
And the question is, we have the probability that it is because I'm just trying to think about it, because we have one of them, but we're trying to find the other. So like we have the probability of the cows having the disease given that they were tested right. We would have that, right? Because that's the percentage, the percent positivity. How right are we in that? So that would be that percent positivity, right? If we're trying to calculate, well, what is the probability that the cow has the disease given that it was tested right?
Okay.
Because if that is not 1, which is always the case, that means there's it's not a perfect test, which is obviously true, right? So there's going to be so that could be a number that we're trying to find. And the number that we could already have is the probability that it is a right test given that the cow has it. Would we know that? It's something like that. It's something like that.
You could, because that would just be a property. Like the probability of it being a correct positive given that the cow has the disease is just a condition on like the accuracy of the test itself. And so that's like a manufacturing thing where they're like, okay, this is how often it's actually right. But
Okay. Yeah, so I was able to pull it up.
Finding it the other way around would be what.
Yeah. So it's one of the
for.
ways that you want it, and the other way. See. What we have. Wait, B denote that the cow has it. Test positive given that the cow has it. See, that's the thing. So we have one of them. We already have one of the probabilities. That's the only way to do it. The only way to actually conduct Bayes' theorem is by knowing one of the given probabilities, right? Because you need one of them to solve for the other. So you have, for example, the probability that the test is positive given that the cow has it, and you want to find the percent positivity rate. So you're trying to find the probability that the cow actually has it given that the cow has been tested. So something like that, you can just switch the probability, right? And how do you get all of this? This is all just got from numbers, right? All this percentage, all this data is all just got from actual numbers that they've sat and tested, and they were able to conclude this data. So, I mean, that's kind of why I think I'm just nerding out, but I just love statistics because of this reason, and this reason mainly, right? It takes in raw data. You can't say it's wrong, but here's the thing. Here's the thing. Here's where I wanted to say this. Here's kind of what I wanted to bring it into. Statistics is a very powerful tool, and with this tool, it can be greatly mismanaged. What I mean by that, there's so many times where you see certain articles citing certain statistics, some insane, like 80% of something, some like, you know what I mean? Like some crazy article. Let me just recommend this video to everyone. There's this video on YouTube. What's his name? By Zach Starr. And it's called How Easy It Is to Lie with Statistics, or Lying with Statistics, or something like that. And that's basically the video immediately I thought of when I said you can't lie with it. That's the exact same thing I thought of. So I would recommend all you guys watch it because it shows you the power of how easy it is to lie. Because if you have a certain sample, you can affect that sample, if you have that power without letting the audience know or whoever that you're telling that statistic to that you have mediated in that sample, you can completely fabricate data. And there have been instances, again, I do not recall this, sorry for my ignorance, but it is on the video. I will recommend, we should definitely link it in the description. It's a beautiful video by Zach Starr. And again, it basically, I believe it even gives an example of some court case where someone was tried and put away for some crazy stuff because of a wrong or an incorrect statistical interpretation.
Wow.
Because it was like the incorrect way of interpreting the data that led them to incarcerate him, which led to all this stuff. So believe me, it's a crazy story, and I just wanted to bring it up, but it's a very powerful tool because it all depends on the data that you're bringing in. And not a lot of people are caring about that. You say 70% of Americans are this. Poll taken with 1,000 people. What do you mean? How can you do that? You know what I mean? Like it's a very, and those 1,000 people will be in the same area. Like, you can't do that. Like, it has to be a random, you know what I mean? So there are a lot of studies, there are a lot of things that can mess with you, convince you otherwise because of these numbers. And these numbers are so powerful and they can lie so easily because of just data, because of how data can be collected, because of how different data can be, random data, all this stuff. I mean, we're definitely going to get into it, but I just wanted to get into that rant a little bit about how important statistics is.
No, it's really important, especially because everybody just believes everything, and it's insane. So
that's true. That's the world we live in.
If you just throw out like 85%, blah blah blah, people be like, "Damn, that sounds like it's right."
Yep, for sure.
Even if it doesn't even sound right, they'll be like, "He wrote that down, so like that's probably true." Mm-hmm. Anyways, anything. Anyone can write anything, but yeah,
that's the tough world we live in, right? That's the statistical. That's the disadvantage. With the advantage of how awesome it is, it's so cool, helps you with so many things, right? I mean, it allows businesses, it allows countries to still function. Math, like basic, like statistical stuff, using these aggregate data slots. So it's important, and it's really cool to get Parker to say that it's important. I really appreciate it. That's
No, I mean, obviously I know stats
no, I'm playing.
is
I'm joking,
important.
of course. Yeah.
Listen, stats is a really big part of astrophysics because
It is.
the main thing you do in astrophysics is collect data from the sky.
You're right.
And then you interpret it. Like basically everything, all the theories and all of the things we know for sure comes from collecting data from the sky and analyzing that data.
Mm-hmm.
You know, if it wasn't for telescopes and Galileo, you know, making all these crazy devices, like just take a look at the sky at night and try to deduce facts about the stars and black holes. You know, you can't really do that. You need to collect data. You need some kind of tool that can see in different electromagnetic intervals and all that stuff, and then boom, as soon as you have data, you have statistics that you have to worry about.
Now, with this data comes along some responsibility, right? Not always do we have only require the raw data. Sometimes we may want combinations of the data. For example, you roll two dice, or two dice is not right. Dice. Two dice. You roll two dice. Die.
To die.
Die. Yes. What am I saying? You roll two die. You want to know what is the probability that the sum will be 6 or 5 or 7 or whatever. What you do there is that's when we start to introduce what I love and a very fundamental concept in statistics, the random variable. It's not, even though it is called random, I don't even know why. I mean, it is random. It is inherently random, but listen to what it is, right? So a random variable, the essence of it, is basically to take a distribution, or to take a number, to take an event, let me say, and to spit out an associated probability, basically. Not directly. Let me fully get the, what am I trying to say here? There's like a whole thing that goes from random variable. It takes in a certain information. What does it take in? It takes in sample space. It takes in that. It gives you a number. No, wait. I'm messing up here. Because it takes up the sample and it spits out a number on the real line, right? And the idea behind this variable is that it is estimating your data. That's the thing. So what we do is there's no real value for the sum of these two die, right? Like we have X here, we have Y here. Let's say X represents the number on this die, Y represents the number on this die. There's no real number to represent the both. So we say,
Dice.
Let's create, sorry?
Dice.
You know what I mean, man? So let's say we create a variable S, and that will be the discrete random variable because they're discrete variables, right? They're discrete numbers. It's going to be the discrete random variable that represents the sum of both of these, of the faces of the two die, right? So the idea behind a random variable is to basically simulate a real life situation, right? To take in something that has happened and to spit out an associated mathematical relationship, right? And the power of the random variable is, well, what do we do from that? Remember, it takes in information from the sample space. It spits it out to the real numbers. It spits it out to R. It's basically a function. It is a function, right? It takes in a set, which is the sample space, and it spits out a number on the real line, right? So it is a function. And what we do with this, the random variable itself is not that important. What's important is what we do with the random variable. Because with the random variable, we are now allowed to conclude probabilities. So with the random variable, we pass it through a probability function, and we're going to get into this in a second. We pass it through a probability function, and then we spit out a number anywhere from 0 to 1. That's the whole idea. So let me give you an example, because examples are where this is at, right?
Hold on.
Yes.
I just remember being in a workshop that we had.
Yeah.
It was like an Astro workshop. Oh, wait. Okay. Yeah.
Oh, Mike.
Yeah.
Okay.
So we had this astro workshop where we were talking about astrostatistics.
Oh, that's
And
cool.
this was, I mean, you were there.
Oh no, I
you
remember
were
this one.
there.
Of course, I remember this one.
Yeah.
I was I was
so
confused. Yes, continue.
she started talking about random variables and me not knowing stats. I was like, okay. Nice. But she said something that made me understand it like immediately. She's like, random variable, you denote it with like a capital X, and then
Capital letter, not. I mean, yeah.
yeah,
letter.
capital letter, and then a realization of that random variable is denoted by a small
Lowercase.
by a lowercase of that same letter. And then that kind of clicked in my head where I was like, the random variable represents like, it's just like a general
A theoretical
representation of anything that can come out of your experiment.
Exactly.
It's not anything specific. But once you actually do the experiment and you get a realization of that variable, then boom, you add it to your collected data.
Mm-hmm.
From there, you can do your experimental or what am I trying to you can calculate your outcomes, right?
Yeah.
You can do your experimental mean, median, standard deviation, which we haven't talked about yet.
Mm-hmm.
But oh man, there's so much to talk about. I want to talk about like the theoretical mean and the what was that thing we had to do for the one lab? The confidence intervals. Yeah.
That would be. Do you want to do that? Let's not do that.
Let's not do that.
Yeah. Well, we can still do that. We can definitely do that. But like we're talking about random variables, and I kind of like that realization versus the variable itself, right? Because I mean that is important. Because that's what I was trying to say, right? The random variable is a theoretical value, and it's basically the idea is okay with this variable. Now here's the power. Here's the true power of the random variable. Graph every random variable there is, basically. Now, in a discrete situation, now here's where it switches up. Here's where discrete and continuous are a little different. Usually, you just apply, like, if you're summing up in a discrete, you integrate in a continuous. And it is not exactly similar. So here's the difference. In a discrete situation, we have random variables, right? And then in every scenario has, again, what I wanted to talk about, and again, what we did talk about in last week's episode, the probability function. The probability function is basically a function that takes in a value and it says, well, what is the probability of that event occurring? And that value, again, is an event. It's not an actual, it can be represented as a number, but again, it's an event. It's an event occurring. So maybe a 2 represents this happening, a 3 represents something else happening, something like that. It's an event. So that's your probability function. Now, in a discrete distribution, right, which is basically that dice example that I gave, right? If we have 2 die, it's a discrete distribution because there are a finite number of possible events occurring. So in a discrete distribution, our probability or our random variables will spit out a probability. If you basically graph the distribution of all the possible these random variables, that means how many times does 2 come up? How many times does 3 come up? How many times does 4 come up? How many times does 6 come up? If you graph the number of time, basically the frequency versus the sum. So the random variable is on the x-axis, the frequency is on the y-axis. If you graph that, what you will get is a probability distribution. And that is a consequence of the discrete random variable. That you spit it out, you apply it to your sample space, and it basically spits out a probability because it's graphed against frequency. And that's really cool. And that's really impressive for discrete cases. Moving on to the continuous case, we have something really interesting, the probability density function. This is where there's a little bit of a difference. The random variable doesn't directly spit into the probability. Before we get into that, let me give you a little bit of a break, though, from my voice.
Yeah. So I wanted to say something about continuous distributions.
Yeah, go for it.
Because I remember I always have so many stories about being in
let's hear
class.
it.
But I was in class, and technically I was right, but technically I was wrong. But this was our tutorial for thermodynamics, and our TA asked. He says, "What is the probability that I forget what it was, but he's like, what is the probability that like your particle has this velocity?" And I said it was 0. Probability 0. And he's like, come on guys, don't be stupid. I'm like, what? It's a continuous distribution.
Yes.
So technically I was right.
Yes.
The thing about continuous distributions is that you have an infinite amount of like options. For example, if we're talking about the height of people, you know, you're not exactly 5'10". You are 5.1 or 5'10", 0.0125, whatever. You know, your exact height is not 5'10".
Right.
And technically on a continuous distribution, your exact height is somewhere along the real numbers. And the probability, you know, when you calculate the probability, you do like the number of times the event happens divided by the total tries or whatever. You technically the total amount of possibilities that you have for your height is infinite. So the probability that you have an exact height is 0. But once again, we talked about integration and probability density. If you graph your probability density function, you can say something about probabilities when you talk about intervals. Because the probability density function integrates, if you go from minus infinity to plus infinity, it'll be 1. That's how you get some
property.
Yeah, right? It's a fundamental property, because if you know, the one thing that we always talk about is the probability density of the double slit experiment, which is inherently tied to the intensity of the light that gets projected onto the background. And if you say that the intensity of the light is 1, even like the incident beam, the intensity of that beam is 1, automatically, it doesn't matter where the light ends up, if you sum up the total intensity of the waves in the interference pattern, it will have to sum up to 1, because you can't create more light just by sending it through 2 slits, right? Yeah. That's just, and yeah, this ties back to probability density, because the brightness or the intensity of the light on your screen is tied to how probable it is for a photon to land there. Obviously, if a spot on your screen is brighter than another spot, then more photons are hitting that spot, so automatically it's more probable that it lands there. But the point of this entire photon discussion is that you have a probability density function. The probability has to sum up to 1, or else it doesn't make sense. Because if you're sending a photon through, it's gonna land somewhere, which means there's 100% probability that it lands, period. You want to know where it lands. And so what you do is you integrate. You want to say, okay, what's the probability it lands between this spot and this spot? You integrate, and the area, you know, the area under the graph is going to be x, and then you divide by the total area, which is just 1. So x represents the probability itself, because you just divide by 1. And same thing goes with any other probability density function. You have to say, okay, the electron, the position of the electron, what's the probability it's between, what's that? What's small a? It's a length, you know, on the probability. It's not angstrom.
No, yeah, like, that's what I was thinking of, but you said small a.
It's a small a. It's like, it's that one, it's like the peak of the distribution. Anyways, point is, you get it. You got to integrate between 2 points.
Yeah, 2 points. So yeah, importance, right? And continuous distributions are really important there because of that integral, right? They're differentiating between the integral part and the summation in the discrete notion. And integration and well, this whole probability thing I think ties in really well to quantum mechanics. But before we get in there, because I just wanted to touch it later, types of distributions, right? So we were continuing on the discrete or the continuous random variable, which becomes very cool because, as you just said, we have now to integrate it to find the probability. So it's not directly spitting out a probability, right? But what's interesting about this also, as you mentioned, is that we no longer can quantify a singular event. We can't say this. It has to be an interval of events, right? Which gives us a few examples here. So before we get into continuous, because I know that it was, let's get into little examples of discrete distributions, right? So you have, I think, just little here, classic Bernoulli distribution. That means it's either a yes or a no. So it's a 1 or a 0, basically. Like that, like the probability is either can happen or it won't. So it's very simple. That's your easiest example of a discrete distribution. Another example, very famous, is a binomial distribution. You might have heard this one. The number of trials and the number of successes, right? So like, let's say you want 4 heads in 6 coin flips or something like that, right? It's a discrete number. And there's literally a formula that you can just use to calculate it. You know, it's no pressure completely taken off you. Just put it in this thing, and that's the binomial distribution. That's the binomial formula, actually, to basically, again, tell the number of combinations between both of these, between the number of trials and the number of successes, right? How many do you need to satisfy those number of successes? And you also, and in the continuous side, we have your famous uniform distribution, which is just going to be flat. For example, let's say, I'm just thinking of an example, like, I don't know, like something can only be here, you know, and like nowhere else kind of thing. Like, I'm just trying to think, like, let's say, I don't know, this is really stupid. Let's say you're swimming in a pool. What's the probability that you're, okay, this is a really stupid thing. But like, if you were to graph the proper probability distribution for the whole length of the pool, you would be in the pool. So your probability would be 1, right? And then when you're out of the pool, your probability would go back to 0. So the idea is that the probability is uniform for the whole sample space.
Okay.
Right? Or for the whole random variable space. Interesting when we get into continuous distributions. 2 of them. You're going to like the next one. The exponential distribution. This is always when we're masking any amount of time. So let's say we're like the amount of time that a customer was talking to someone represents an exponential distribution. Interestingly enough, everything relating to time, everything relating to any amount of something passing, any average rate would be an exponential distribution. And this is a continuous distribution. Why? Let's say you're waiting for a bus. You don't know the exact time that the bus will arrive. It can arrive at 5 o'clock. It can arrive at 5 o'clock in 1 millisecond or 1 micromillisecond. You know what I mean? So it can be any amount. So what you do with all of this is you take the theoretical values as you calculate it and you put them onto a graph. And what that graph represents is basically your distribution. And if you graph an exponential distribution, it will look like a graph of an exponential distribution, right? So it's not your e to the x, but it's like your, for example, you may, what's the famous example? Like 1 over x would kind of look like that, right? Like the exponential
hold on.
distribution.
I'm thinking about your example, and I don't think that's a good example, because what if the bus, like, if you're waiting for the bus, I feel like that would be a normal distribution, right? Because most of the time it would arrive on time, but it might arrive early or it might arrive late, right? But it would be distributed as like a normal distribution.
Well, all distributions relating to time usually, okay, well, I guess in that situation, if you know the time the bus is going to arrive, that's a little different.
Yeah.
Because then you have that value.
That's also not true, though.
No, but exponential distributions actually approach normal distributions on high levels. So it depends on the number of data that you're also sampling as well, right? So, I mean, exponential is usually used, again, for like any waiting period. Like that's usually how we did it. Any waiting period, like if you have the average number of thing, like you get to the bus stop, the average time to wait, let's say if you get is like 5 minutes, something like that, you have an average number. The closer you get to it, the farther it gets away, stuff like that. There's a whole way that we represent it, and it's an exponential distribution. Very, very, very popular to use. And again, how we actually find the probability is simply by integrating 2 different random variables. We want to find what's the probability that, I'm waiting over 7 minutes. So 7 to infinity. I integrate that, and that's my probability, right? So I mean, it's a very intuitive thing to understand, how to get to the probability.
So you're saying that there's a chance that my bus shows up 1,000,000 years late?
There is a probability, right? It is a probability that can be represented. So that's the only thing, right? Probability gets important there. Yeah, see, I'm looking at right here, like a quick bus example. And they have an exponential distribution with a parameter. Yes, that's what I'm saying. So usually we use exponential distributions if there's any time limit involved. But let's get to the fun one, because I know you want to talk about this one. The normal distribution. This is a very famous continuous distribution that, again, basically you're just dumping these random variables onto a graph and you're looking at what it looks like. So to be honest, I mean, I don't know, maybe if this is in a clip, hopefully we can maybe put like the pictures on the side of all these distributions as we're talking about them. So it's just like exponential, normal, stuff like that, so you can see it and immediately think about it. But if you have them in your head, then it may make a lot more sense. So the normal distribution. Get into it.
Yeah.
Want to get into it?
This is also called a Gaussian distribution.
The bell curve.
It's the most, I guess popular. It appears in nature literally everywhere. If you're looking at, I don't know why I'm thinking of this, but let's say like the thickness of a tree, for example. You pick like one species of a tree and you just go into the forest and you measure the thicknesses of their trunks. It's probably going to be a normal distribution, right? Don't quote me on that, but if we're talking about like the same age of the tree, same soil, okay. Anyways, essentially, the bell curve can be described mathematically by the most. I mean, I enjoy this function because you can't integrate it with elementary integration techniques. But it's essentially like a constant times e to the minus x squared. Of course, I'm not putting in the details about like the mean and the variation and all that. But just a fun fact: you can't find the antiderivative with elementary integration techniques. Point is, it looks like a bell, and you can normalize it so that the area under that curve is equal to 1.
That's the standard norm. Oh, well, no, wait, that's always true. The area under is always 1, right? Because that's just a probability.
Yeah.
Property.
And I think the cool thing about it is that essentially anything is I know this is not true, but so many things are distributed normally that it's so versatile, and you can obviously there's a mean, and it's also symmetric, which is a very important property. There's a mean, and there's also
not always. It can be a skewed normal.
It can be skewed.
Yeah.
But I'm talking just about the normal.
Standard. Okay, that's different. Yes. Yeah, there are also types of normals, right? So your standard distribution, your standard normal is what we're actually more familiar with and what we usually do. So when you were talking about the Z-scores, right? So that's where really it shows power. So what is the Z-score, right? So it's basically a way, it's also called standardizing. So wait, first of all, before we get into this, did we even talk about standard deviation?
No,
we didn't. Idiots. We should have done this when we were talking about sets. Because we did the mean and everything. We just forgot about standard deviation. So
well, standard deviation, essentially, just think about it as the width of your graph. If your data is very concentrated around one point, most likely the mean, and your bell curve is very sharp, then your standard deviation is very small, because on average the data does not deviate very much from one spot. But if your curve is very wide,
bless you, bless you. You get.
But if your curve is really wide, then it's in the name. You know what I mean? The data deviates from the mean. So
but I mean, like you were talking about like graphs and stuff, but like I mean, we're just talking about straight raw data. Well, what is standard? Like if you have a 1, 2, 3, 4, 5, 6, what is standard deviation? Well,
I mean, Same thing.
Well, I guess,
kind of
yeah. I mean,
applies what
I
said.
guess you can't picture it visually too. The visual learners might have liked that graph description there. But if you haven't seen a bell curve before, which I think most of you have, but if you haven't, then a standard, again, standard deviation, it's also measure of uncertainty. That's also really important, right? So the literal formula of the standard deviation is basically finding the mean squared distance. So it's basically like finding the error between the values. So like all the random variables. So x, basically all the values on the x-axis versus the mean. So you're basically averaging out all the x values and you're seeing the distance between all of them to the mean. And you're trying to see, well, is it symmetric? How small is it? How far is it? The smaller the standard deviation, now you can go into the graph thing. The smaller the standard deviation, the closer the data will be, right? And inherently, if you're graphing it, it's just going to be like it's going to be like a higher peak. And it's just going to be a more concentrated data set. And if you have a larger standard deviation, again, you're just going to have the opposite. But what is it? So in those rulers is a bad example. Let's say you're measuring something, like you're measuring current. In all devices, there is going to be some measuring error. Now, human error is different, but there's instrument error. All instruments have fundamentally some amount of error. And uncertainty is something that you cannot negate, cannot forget. Believe me, like anyone who has done any labs, physics labs, both of us have, know how important uncertainty is. Without uncertainty, your calculation is meaningless. Your ruler is 2 centimeters, wrong. It's 2 plus or minus 0.01 centimeters. It's always that uncertainty is a very important addition to any measurement. Why? Because every instrument, everything that you use has some level of uncertainty. Now, quantum uncertainty, I know I just thought of this, so I had to say it, is different. You may be thinking, oh, even atoms, yeah, that's a different thing. That you cannot go out of, you cannot break that level of uncertainty. This uncertainty, you can tweak, you can change, depending on your data set, depending on your instrument. If you use a more precise instrument, for example, your uncertainty will lessen. If you use, let's say, a more concentrated data set, your standard deviation will change. So you can tweak it around here and there, right? And basically it's just a measure of how spread out all the data values are, right? It's just measuring that. And now going back to the standard normal and why that is so important is because the standard normal, it does two things. So in a normal distribution, it has a mean, which is an average, and it has a standard deviation, right? Which is basically, as we just said, like how spread out the data is. In a standard normal, the mean is moved to 0. And you might be like, what? So if it's like at 50, just subtract everything from 50. Very, very simple. Now here's the confusing part. The standard deviation of a standard normal is 1. Now obviously every data set does not have a standard deviation of 1. So we can't just subtract 50 from everything. And this is the Z-score formula. This is the Z-score thing that you were talking about, Parker, in the beginning. That's super broken and super cool. And this is called standardizing. And you take any data and you create a Z-score. You standardize the data. That means you're making it into a standard normal. And again, this is you do this from a normal distribution. I'm gonna get into how you can also do it with other ones. But for now, with a normal distribution, anything you have, you plug the numbers into a formula. Again, we're not going to get into that here. You plug the numbers in, and it basically spits out a value on the standard normal curve. Now, the advantage of this is that any point, you can now compare any, and literally this is the definition of any normal graph, normal distribution whatsoever, with any amount of data representing any amount of information, and you can put them on the exact same curve. So that's the power that gives you, right? And standardizing, understanding that Z-score is also important because of, okay, I guess we didn't really get into this, but you know how we were talking about when we calculate probability, well, we're integrating things, right? So usually when we want to find, the reason we find the z-score is because we're finding, okay, what's the probability that the realization or the values are less than the z-score or greater than the z-score. And there's actually a table, a z-score table, which actually has all of these values, which is why the standard normal is so important. Because I think from as long as statistics goes back, we've had a z-score table, a way of standardizing these normal units, right? To make it succinct so that any data set that you have, any data set whatsoever, again, we're going to get into how it can be approximated as a normal in a sec, but also, any data set, any data set can be brought onto a z-score, which then can lead you to find the probability for that event. Any data set, right? And that's your big advantage, just the succinct table.
I was just going to say this is also assuming it's normally distributed, but yeah.
Yes, of course. This is assuming it's normally distributed, but here's the fun part. The central limit theorem. Yes, that's the fun part. So the central limit theorem states, if a data set has a mean and a variance. Now, variance is basically the square of the standard deviation, right? Again, why is it important? Because it's important in math, not really much in how we're talking. That's why standard deviation makes more sense. But the central limit theorem basically says, if a distribution has a mean and a standard deviation. Now, this is not always true. All distributions don't have a mean and a standard deviation. There's a Cauchy distribution, for example. There's some complicated distributions that don't have either of them, right? And they're very confusing. But anyways, the central limit theorem says any distribution that has a mean, which is an average, and some standard deviation, that means there's some level of spread from the middle, anything at all, right? And this can be an exponential, this can be it can't be discrete, any continuous distribution, really. As you take more and more data, so this is basically a limit. It's called a central limit theorem because it's a limit. So it basically says the limit as the number of points, the number of data points goes to infinity. This distribution, whatever it is that has a mean and a variation, goes to the standard normal. Now, the standard normal, again, goes to the normal with particular parameters. Again, that's just the mathematics of it. But the power of what I just said means that most, again, not every, but most distributions that represent something in real life, something that has a mean, something that has a standard deviation, can be approximated to be a normal. And then from the normal, we can approximate it to a or not approximate it, but we can get it to a standard normal, and then we can calculate an event, the probability of any event. Broken, isn't it? Central limit theorem.
Absolutely incredible.
Absolutely incredible.
Well,
really crazy thing there.
We learned a lot today.
Yo, we didn't talk about expectation values at all.
Expectation values. Well,
quantum mechanics.
It's what you would expect.
It is what you would expect. Expectation values are really cool. Because
I think we have enough.
It's not the mean. Well, it is in some situations.
It is.
It is. It is in some situations. It is in some situations.
In some situations.
The expectation value is basically, what do you expect to get out of this? I guess that is actually the best way to put it. And a good way to tally it and a good way to count this, a good example to give as well, is in, for example, a blackjack game. Now, I believe the real calculation has been done. I don't know if it was for this blackjack game, but it was for something like that, or some game, something gambling related. And when you actually do the math behind it, the expectation value is negative. So what that means is you put any amount of money in. What the expectation value does in this particular function, in this, let's say, a gambling example, what this expectation value does, it calculates the average win or loss amount from you. So playing every game equally likely, basically the mathematical ideal scenario, would you win or lose? And obviously you may know where this is going. Every single casino game has a negative expectation value, right? Because the house makes money.
Actually, except for poker.
Oh, poker. Okay, house makes money. No, make no money in poker. Poker is against players.
No, the house does make money because they take a cut from the pot, like a percentage.
That's different.
But if you were to just play like the game of poker, like just between people, there is no expectation value.
I would assume so. Yes, that makes sense. I'm talking about all the casino games where the house is involved. I guess if they're just taking an amount that's not really involved, but like I get it. But I'm saying like where they're directly playing, all of them have a negative expectation value because that's where they make money. And that's the thing. No one really thinks about that. They're like, oh, I can beat the house. Yeah, today, tomorrow. Yeah. But average it for 10 years, you won't. So that's the thing.
The expectation value is actually just the value of the event. So, for example, if you're rolling die,
same mistake.
If you're rolling some die, the event would be like getting a 6 or getting an 11. So you take that value and you multiply it by the probability of getting that value, and then what you do is you take the sum for every single possible outcome.
A weighted average. Nice way to think about it.
Yeah, essentially a weighted average. And what you get at the end is the expectation value. The thing about expectation values is that they do transfer over to continuous distributions. But as we've talked about before, when you have a summation in the discrete world and you want to translate that to the continuous world, it goes to an integral. So essentially, it does go against what I said earlier, but you would take, because it doesn't make sense, right? In the discrete world, what you do is you multiply the probability with the value of the event or whatever.
Yeah.
In the continuous world, you can't really do that one by one because each probability would end up being 0. But mathematically, it still works out by taking the integral.
Integrals.
And this does this is used a lot in quantum mechanics because the expectation value, for example, the momentum of a particle or the position of a particle is very how do you say, à la mode? It's like popular, like to do.
One guy who doesn't speak French would know it. But yeah, I mean, the expectation value is super cool in quantum mechanics, right? Like super, like it's just telling you like the average value of some certain thing, right? And there's a formula. There's always a formula. There's literally a formula relating to it. You just plug in your wave function. So whatever, again, for those haven't listened to the quantum mechanics episodes, quick, just a function that describes the state of your particle. So you just plug that function in and boom, you get the average value of whatever you want. Right, so it's pretty cool.
Let me know if I'm tripping right now.
Yes.
But to find the expectation value of some observable, you just stick it between the two.
Yes.
The two broad.
Yes. Exactly. Yes.
Is that okay?
Yeah. We remember.
Wait, can you explain it? Do you remember?
Math, but yeah, sorry.
Do you remember? Do you want to explain it? Because I don't remember.
We don't have to get into that.
Oh, okay. If you don't want to.
Do we have? Okay. Is it? Wait, we put it, the expectation, we put it in with the wave function, right? Exactly. Okay, so let me explain. In quantum mechanics, if you want to find the expectation value of a certain operator or a certain measurement, so for example, you're trying to find the average position, you're trying to find on average where would this particle be? On average, how much momentum would this particle have? What we do is we put these operators. Now, in quantum mechanics, everything becomes an operator, right? And we've spoken about this before, I believe. So we put this operator and we squish it. Now, again, this is a lot very mathematical. We haven't really got into Dirac notation whatsoever. But we basically squish it between two wave functions. So the wave function of this system. So there's a system, right, that has a wave function. The wave function is, again, describing all the states, the possible states of the system. So on like 0.5% chance it can be this, 0.5% chance it can be this, whatever. Like it's describing all those possible states. So whatever operator we're trying to find the expectation value of, so the average value of something, we're basically squishing it in between the system and the average state, the state of the system itself. Now, I don't really know how the math works, like why this works. Like why we squish it in between? Do you know why we do that?
we saw why in the like while we were studying this.
No, definitely. I don't remember it though.
I don't
remember it
remember
off the top of my head. I don't
No, but
really
it's-
remember.
it's mathematical though. Like
Yeah,
if
no,
you-
of course. No, of course. It is highly mathematical. It is highly mathematical because all of these are just theoretical states of where the particle can be, what state the particle could be in, and it's just putting these things together and then spitting something out. Right?
I mean, it's pretty. It's not that hard actually. All you have to do is, let's say your observable is like the spin of an electron in the z direction. What you do when you by definition of the expectation value, you multiply the probability by the value itself. So you do like h bar over 2 times the probability, and the probability is the modulus squared of the wave function inner product with each. You either have plus spin or down spin.
Yeah.
And then if you just expand that, like the mod squared, the mod squared is just equal to the inner product multiplied by the conjugate. You can factor out whatever, and then it just ends up being like the state sandwiched into the
Okay, so whoever has done a little bit of Dirac notation, I don't know even I hardly followed that, so if anyone did follow that, props to you. But so that's a little bit of where expectation value can become very important in quantum mechanics. And the whole ordeal of quantum mechanics is based on statistics, is based on probability. Because the Copenhagen interpretation of quantum mechanics, which is the modern interpretation, right? We have the Copenhagen, we have the many worlds. Those are the two popular ones. We've spoken about them before. And the current one that we use is the Copenhagen interpretation. And we know that to be a probabilistic interpretation of quantum mechanics. It is literally defined as a probability. Everything in quantum mechanics is defined as a probability. In fact, the most insane thing about the wave function, and again, we spoke about this, I remember, in the last week's episode, but the really cool thing about the wave function is that when we square it, we get the probability of the particle or the system being in that particular state. So the wave function that really cracked up there, but the wave function by itself doesn't really represent much, right? Like, it represents something when we apply it to something else. By itself, it means nothing. And again, when using the statistical approach, when you square it, we now get the probability, kind of leading you to believe that because everything in quantum mechanics stems off from the wave function. Everything stems off from the wave function. And the fact that the wave function is inherently tied to the probability function, it kind of just tells you a little bit about the nature of quantum mechanics, right? It's all probabilistic, and using like kind of the knowledge of kind of what we spoke about today, like a little bit of what we spoke about today, can be used in quantum mechanics kind of to understand these average values, these expected values, and because it's really important, especially when you have an electron flying away a few kilometers. You're like, where can it be? Be here. So equally important, right? Yeah.
So this has been a good conversation.
This has been
statistic.
You already know I love talking about statistics. Like, I don't know, you guys definitely heard me a lot more in this episode because I just love this topic.
He is the stats major here.
Yeah,
anyways.
for sure. Who knows? There are always more things to talk about. We can always do a next one, but I think this was a cool conversation. A little bit about why statistics is important, how it can be mistreated, and some cool things about data. Hopefully got you guys interested in stats. Yeah.
Let us know if you have any suggestions. I do remember we had one suggestion to do an episode on discrete math, which sounds pretty interesting, like sequences, series, summations, all that stuff.
That would be crazy.
We might do that next week.
Yes, that's a nice idea, actually. We've done a lot of math episodes, though, back to back. Maybe get into physics. I don't know. We'll see. We'll think about it. As always, though, as you already mentioned, just literally DM us. To be honest, like, even though we do check our email, we definitely do. I think we've been responding a lot to Instagram lately, and I think that's just a natural thing because of the sheer number of emails we get, from like all types of sources, not only obviously you, but so obviously, not obviously, but Instagram would be an awesome platform to talk to you guys on. And if you want to suggest anything, that would be cool as well. Email is fine, but if you have Instagram, it would be better. I'll just put it out there for sure.
Mm-hmm.
And before I forget, giveaway. Go tag your friends. Go put your favorite episode down there. Go follow the podcast. And hopefully you get it. It's going to be so exciting. I'm so excited to announce it. We may do it on IG Live, to be honest. I kind of think we're just going to random comment generate that on IG Live.
Yeah.
And just who knows? It's going to be super cool. So stay tuned for sure.
Yeah. So, if you enjoyed this episode, make sure to follow us wherever you're listening to this. And also come on to YouTube, look at the video, leave a like, subscribe. Other than that, I am your host, Parker. This has been episode number 71. I'll say it again. I am your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.
See ya.